right, we want to talk about half-life here today. And the thing with half-life that we have to deal with is radioactivity. And remembering there's three kinds. We have alpha, beta, and gamma. Alpha being those helium nuclei with a 2 plus charge. Beta meaning our high energy electron, and gamma meaning our high energy photon. We measure radioactivity and how many emissions there are per unit time. And the typical unit is the becquerel, which is 1 emission per second. Tool-wise, if we want to measure it, it's with a Geiger counter. So some factors that affect radioactivity. Is there a way to change the rate? What affects the rate? And Marie Curie studied that question. She wondered if the rate of nuclear emissions could be affected by things that affect chemical reactions. Things like temperature, pressure, or chemical bonding. And what she found out, in fact, was no. None of them do, but a little bit about how. Right? If we start with a plutonium pellet, 500 becquerels, so 500 emissions per second. Let's heat it up. You'd think if we heat it, that should affect the radioactivity, but it does not. Cold or hot, rate was the same. Temperature has no effect. What about pressure? If we put it under pressure, maybe it won't be able to decay as quickly. Nope. Pressure has no effect. What about chemical bonding? Nope. Chemical bonding has no effect. If I make plutonium into plutonium dioxide, no effect. So what does? And there's really only two. The mass, so how much of your sample there is, which sort of makes sense. We'll talk about that in a minute. And the half-life. Now, when we talk about the half-life, that really is code for what kind of material is it, specifically what isotope is it. Okay, moving on. More mass in the sample, the more nuclei that can decay. And there's, in fact, a direct relationship between activity and mass. And that sort of should make sense because the higher the mass, the higher the number of nuclei. The more nuclei there are, the more likely there is going to be that they decay. So small mass, small number of nuclei, large mass, large number of nuclei, more emissions. Half-life. So we use the symbol T1/2 to refer to half-life, and it's defined as the time that's required for half of the atoms in the sample, half the mass, to decay or to transmute to different atoms. Longer the half-life, the more time required for it to decay. And each radioisotope has a unique half-life. So think about thorium-234, half-life of 24 days. T1/2 is 24 days. That means 24 days, half of it's going to be gone. Now we got to think carefully because you might be tempted to go, oh, 24 days, half of it's gone. That means 48 days, it's all gone. But no. Let's look at a picture. Those pictures are nice. So day 0, 100% thorium-234. 1 half-life later, 24 days later, 50% thorium-234, 50% other elements. Another half-life, so 48 days after we started. We now have 50% of the 50% turned into other elements, and then we're left with 50% of the 50%, or 25%. So looking at the picture, right, day 1, well, we've got 100%. And it's going to drop down to 50% after 24 days. And then half of the half goes away, and we're left with half of the half after 48 days. And this continues. And if we wanted to graph it, our graph is going to look something like this. Now, it says 98, it should be 96. So again, here I've put the points in already, but day 1, 100% of the sample is there. Day 0 actually is how we refer to it, right? This is at the very start. After 1 half-life, 50% of the sample remains. 2 half-lives, 48 days, 50% of the 50% remains. After 3 half-lives, or 72 days, 50% of the 50%, so 50% of the 50% of the 50% remains. Half of the half of the half. After another half-life, the process continues. Half of the half of the half of the half. think I had the right number of halves there. Anyways, and so, yeah, you can see, again, this should be a 96. This should be a 96. You can change those in your slides. Also a 96. Also a 96. Apparently I have trouble with math. Also a 96. This is an exponential decay graph. It's going to keep getting closer and closer to 0. Eventually, functionally, it will be at 0. This is an asymptote. I get it. It's not going to ever be totally 0 mathematically. But at some point, there will be one atom left, and that one atom will decay. Quantization stuff. All right. So you should know, you need to know, shorter the half-life, the faster the material decays. So radioisotopes with a short half-life have greater radioactivity, and they don't last as long. So oxygen-19, half-life of 29 seconds, which means it's highly radioactive. In a matter of minutes, it'll be totally gone, right? 29 seconds, half of it's changed to something else. Another 29 seconds, 75% is gone. Another 29 seconds, 87.5% is gone, and so on. And eventually it gets that there's pretty much nothing left of the original sample. Uranium-235, half-life of 710 million years, which means it's not very radioactive. Now, it is somewhat radioactive, which means if you have a huge sample of uranium-235 and a 0.0001 gram sample of oxygen-19, you could probably figure it out so they'd have about the same activity. But in general, we would say, in this case, uranium-235, much less activity, much less radioactive than oxygen-19. So let's do a little thought experiment. Two radioisotopes, A and B. Half-life of isotope A is 20 days. Half-life for isotope B is 100 days. Which sample would show greater activity? Explain why. Shorter the half-life, the less time required for half of the sample to decay. Means in a given period of time, the isotope with the shorter half-life will have more nuclei going through decay. So if I start with 100 grams, if I start with 100% of isotope A, and I let it decay for 100 days. So I start with 100 days, 20 half-lives, let me try that again, 100 days. And I divide that by 20 days per half-life, which means it's gone through 5 half-lives. So what I'm going to say is, for each half-life, I'm multiplying by 0.5. Right? So this is going to be 100% times, and then 0.5 exponent 5. That's what I really just did up there. All right, 0.5 times 0.5 times 0.5 times 0.5 times 0.5. I'm left with 3.125% of the original stuff. Isotope B, half-life of 100 days. So it's gone through one half-life after that 100 days, which means after 100 days, 50% remains. Right? Or if you really want, this is 100% times 0.5 exponent 1. And this means isotope A has to have more emissions, especially if we stipulated at the beginning that they have the same mass. In fact, it'll have 5 times more emissions. Using the graph on the following page, we want to find the half-life of cesium-137 and then the percent of the sample left after 80 years. So I've done some of the work for us here. I made a nice line going over. I figured out, first of all, we started with 8 times 10 to the negative 3 grams. And I found out half of that. Okay, that's going to be 4. And then I make a line coming across, see where it intersects the graph. And then I trace that straight down, and I find out that my half-life is about 30.5 years. So that's part A Part B then, you say, okay, after 80 years, how much is left? So I go up from 80 years, find where it intersects, and then I'm going to trace this over to here, find where it intersects. It's about 1.2 times 10 to the negative 3. And so I've got 1.2 times 10 to the negative 3 divided by 8 times 10 to the negative 3. So this is how much is left divided by how much we started with. And I get 0.15. And as a percentage, that means I've got 15% left after 80 years. Okay, and again, you can see this step by step if you would like. And lovely, here we go. Now, mathematically, it's an exponential decay equation. So n equals n naught times 0.5 exponent n, where n naught is the original amount, or the original activity, or the original percent of the sample. N is the final amount, or the final activity, or the final percent. And then little n is the number of half-lives. So, how do we calculate the number of half-lives? This is not given on your formula sheet. You have to be able to figure this out. We already actually did this, where little n, the number of half-lives, is equal to t, a little t. This is the total time of the experiment, and t1/2 is the half-life. And you must use the same units for each time. So I can't say, oh, I did the experiment for 100 seconds, and the half-life is given in years. That's not going to give me the right answer. The units have to cancel because the number of half-lives can just be a number. We did this with our fake isotope A and isotope B just a couple of minutes ago, right? Where you've got isotope A, what we said we're going to do 100 has a half-life 20 days, and we ran the experiment for 100 days. And so 100 divided by 20 gave us the number of half-lives, which was 5. So oxygen has a half-life of 29 seconds. Find the time required for the sample's activity to decrease from 1500 becquerels down to 187.5 becquerels. So I'm going to think here, okay, this is my original, this is N naught, this is capital N. I'm looking for little n. Now, there's a few things that you don't have to be able to do for physics 30 that you do have to be able to do for math. So if you know math, you can say, oh, I know this. I can do a logarithmic equation and solve this pretty quickly. I'm going to double check and talk to you about this tomorrow, but as the last I looked, you don't have to be able to solve logarithmic equations. But you do have to be able to do a little bit of guess and check here. So let's take a look here. N is equal to N naught times 0.5 1,500 becquerels is equal to 187.5 exponent N. And this 187.5 should also have units of becquerels. My apologies. All right, well, I'm going to get the 0.5 to the nth power by itself. So I'm going to divide both sides by 187.5. That gets rid of all of my units. And 1,500. And first of all, let's actually use the right. This is an easy mistake to make. So what we have to actually realize is that I labeled this correctly, but that means that number should be there and that number should be there. So let's try again. Okay. 187.5 becquerels is equal to 1,500. 0.5 to the n. Divide by 1,500. Goes away, I am left with 187.5 divided by 1,500, which is 0.12. Struggle here. 0.125 is equal to 0.5 exponent n. I recognize right away is here that 0.125 is the same as 1/8. Right, and so 1/8 is equal to 1/2 to the n, and I realize, n has to be 3. So by guess and check, I can, or by observation, n is equal to 3. So that's 3 half-lives. I'm not quite done. The time required for this to happen is going to be 3 times the half-life, so 3 times 29, which should be 87 seconds. All right, so again, here's what we know. Here's where we plug it in. We've had 3 half-lives go past. Yep, there it is. So we can check that if you want. 1,500 times 0.5 times 0.5 times 0.5 gives us this. You can check it in your calculator. And using this formula, now I more or less just did it in my head. I said, oh, I have 3 half-lives. 3 times that is going to give me the total time for the experiment. But I can use this formula, and it's equal to t divided by t1/2. And I want t, so t is equal to n multiplied by capital T1/2. T is equal to, just like I said there, 3 times 29 seconds. Beautiful. All right, radioisotope has a half-life of 2.5 years. What percentage of the sample has been transmuted to other elements after 4 months? Now, this looks like we don't have enough information, but as soon as you see a percentage, usually, unless they give you something else, usually n naught then is 100%. We are looking now for n. That's what we don't know. We do know that the half-life is 2.5 years. We know that the time of the experiment is 4.0 months. Be careful here. Note that years and months are not the same unit. So how do we change years into months? Well, we multiply by 12. So 2.5 years is the same as, if I recall correctly, 30 months. All right, so the number of half-lives then, n is equal to the time of the experiment divided by the half-life. This should make sense that it's not one complete half-life, right? The half-life is 2.5 years. We've only been at this for 4 months. So n is going to be equal to, time of the experiment is 4.0 months. Not to be confused with 40 months, which I keep wanting to write because I see a 4 and a 0. And then divide that by the half-life of 30 months. So 4 divided by 30, 0.13 repeating. Do not round that. And so in this case, it's just a matter of plugging this into our equation, right? And away we go. So in this case, you can't use the second function comma on your calculator to get the times 10 exponent, because we don't want times 10 exponent. You have to use the little, right above your dividing sign, the little hat thing. So this is going to go into my calculator as n is equal to 100 times, and then a first bracket, 100 times 0.5, little hat, 0.133333333, or second function answer. And make sure we've got 0.5 and then we so what this tells us is that we have 91.17% left. If we want to know how much has been transmuted, it's going to be 100 minus that. So just read the question carefully is the big thing here. Right, so we start with a full sample. Again, we're going through this. We've done all of this work. And then the last little bit, this is the amount of sample remaining. And we want to know how much has gone through decay. So 100 minus that number, 8.8% has gone through decay. And that is it. Thank you.